seminar today, and welcome to our online viewers. Today's guest speaker is Mark Teo, so I will introduce you to him. Mark Teo was previously an NSERC Industrial Scholarship recipient who obtained his BSc in the Chemistry Co-op program, as well as his PhD in Chemistry and Nanotechnology at UBC. Mark has more than 16 years of academic, regulatory, and industrial research and integrated hands-on work experience in radiation, nanotechnology, and occupational health and safety. His experience in radiation includes, but is not limited to, X-rays, lasers, radio frequency, as well as radiation safety programs, dosimetry management programs, inspections, investigations, exposure assessments, and regulatory matters. Mark has also complemented his work experience with professional development coursework related to being the X-ray safety officer, radiation safety officer, and laser safety officer. Currently, Mark has been working as an occupational hygiene officer at WorkSafeBC for more than 8 years and is a member of the Canadian Standards Association Technical Committee on Nanotechnology and Occupational Health and Safety, as well as the Canadian Radiation Protection Association. He is a designated subject matter expert at WorkSafeBC on radiation. Mark is also WorkSafeBC's Variance Acceptance Request Coordinator on radiation matters. He has worked with other subject matter experts in radiation protection, including the BC CDC Radiation Protection Services, Health Canada, and Radiation Safety Institute of Canada. He is also consulted by various employers, workers, regulatory agencies, and other health-related organizations on radiation OHS matters. So on that note, welcome, Mark.
Thank you, everyone, and it's an honor and privilege to be invited to speak at this seminar. So today I'm going to talk about radiation protection, controlling exposure in the workplace. And when I talk about radiation and radiation protection, it's actually a very, very huge field. So here's a quick outline of what I'm going to go through. So I'm going to talk about what is radiation and the different types of radiation. Then I'm going to talk about some of the selected applications of where you can find radiation in the workplace. I'm going to go through, give you a brief overview of the different regulatory requirements as well as the different regulatory organizations that look after radiation health and safety matters. And I go through things like the different exposure limits, some of the adverse health effects, as well as things like how to detect radiation and dosimetry and how to control exposures. And then because this presentation might be a bit long, if we have time, I'll go through one case study or one emerging issue on X-ray imaging in healthcare. And at one of the last slides, I'll also give you some resources that you can consider after this presentation. So what's radiation? Radiation is just a form of energy, and it can be classified into two different forms. The first form is what we call particulate radiation. So to better understand particulate radiation, we need to know the structure of the atom. So I'm sure this will be reviewed to a lot of you. So I just remind myself to use the mouse, not to point at the slide. So as you can see here, here's a pictorial example of what an atom is. So inside here is a nucleus. It contains protons, which has a subatomic particle with a positive charge, and neutrons, which has a neutral charge. And then orbiting around the nucleus, you have electrons, which are negatively charged. So when we talk about particulate radiation, usually we talk about subatomic particles that can be emitted from the nucleus. So some examples, alpha particles. So essentially, it's almost like a helium atom containing 2 protons and 2 neutrons. We have beta particles. Essentially, it actually comes from a neutron that actually splits into a proton and an electron. So the beta particle is analogous to a negatively charged electron. And then we have neutrons that can come out, that can be emitted from the nucleus due to things like nuclear fission and things like that. Okay. The other category of radiation is called electromagnetic radiation. So as you can see in this pictorial graph here, it consists of electric field and a magnetic field in a perpendicular orientation. So this includes things like X-rays, gamma radiation, ultraviolet radiation, microwave, and radio frequency radiation. Okay. So I'm going to talk a bit more about particulate radiation. Just a few key concepts I want you guys to know, or at least to remind you guys. So any atom that becomes unstable wants to become stable. So any unstable atoms is just what we call radioactive, and then in health physics, we usually refer to radioactive atoms to be also, it can also be called radioisotopes and radionuclides. So what are a couple of key things you should know? So again, atoms, unstable atoms want to become stable. So how they do that? They have to emit radiation in a process called radioactive decay. So one important concept in radioactive decay is something called a half-life. So that's the time that it's for radionuclide to lose 50% of its activity. So what's an activity? Activity, these days you use the unit called the becquerel, and that's essentially 1 decay or 1 disintegration per second. So this is an animation which I just kind of created earlier this week. Hopefully it works on this computer. So say, for example, you have 1,000 becquerels of a radioactive isotope called phosphorus-32, and the half-life is 14.3 days. So after the first life, or after around 14 days, as you can see in the animation, it reduces to 500 becquerels. Okay, after going through the second half-life, you got 250 becquerels. The third half-life, it gets reduced by half again, 125 becquerels. Okay, the general rule of thumb of any radioisotope is after 7 half-lives, you only get 1% of its original value in terms of activity. Okay, now some of the older textbooks, they might refer to a unit called the curie or CI. So that's one of the older units you might still see. So a lot of times you need to convert the units curie to the becquerel. So this is the mathematical relationship. 1 curie equals to 7.3 times 10 to the 10 becquerels. Now, with respect to magnetic radiation, you don't need to memorize any math equations. I just want to ensure that you learn 2 main concepts from this slide. The first slide is what is a wavelength, and a wavelength is the distance between the first peak to the next peak of a wavelength. Okay, so why is that important? So that leads me to my second point. As you can see in this equation here, the smaller the wavelength or the shorter the wavelength, the more energy you have. Okay, so why is this important? This is important to help us explain the next slide, which is the electromagnetic spectrum. Okay, as you can see, the shorter the wavelength, the more energy you have. So that's what we call ionizing radiation. Okay, as we go down the wavelength here, the longer the wavelength, it becomes non-ionizing radiation, less energy. Okay, so the more energy, the electromagnetic radiation with more energy, ionizing radiation, that includes things like gamma rays and X-rays and certain parts of the ultraviolet light spectrum. Okay. Non-ionizing includes things like the near ultraviolet spectrum, the visible portion of light, infrared, microwaves, radio, and extremely low frequency. So as you can see in the picture down here, it's a wide variety of applications of where radiation can be found and where radiation can be used. And for the most part, WorkSafeBC, we have regulations for most of non-ionizing radiation and all of ionizing radiation. One notable exception is that when we come to power lines, like 60 hertz of electromagnetic radiation, we don't have any specific regulations or specific exposure limits. So that's something to keep in mind. Okay. So what are some things you should know in regards to ionizing radiation versus non-ionizing radiation, especially when it comes to the potential adverse health effects? So keep in mind, ionizing radiation has a lot of energy. So essentially it has sufficient energy to knock out electrons out of the atom it strikes. So essentially you can ionize atoms. Okay. Another thing you should know about ionizing radiation, it can break water molecules. So it can form free radicals, which can cause some chaos in the body. Okay. So another thing you should know about is how ionizing radiation affects the cell. Okay, so there's 3 ways where ionizing radiation can affect the cell. The first way is when the DNA is damaged, but the DNA can be repaired properly. The second scenario is that the DNA can be damaged, such that the damage is so severe that the cell actually dies. And this comes to what we call the deterministic effects. So what does that mean? So it means that severity of the adverse health effects increases with the radiation dose received. Okay, so this produces things like radiation burns, radiation sickness, which includes symptoms like vomiting, internal bleeding, very, very nasty stuff, and in worst case scenario, fatality. Okay, so deterministic effects we usually think of very, very short-term acute high exposures to radiation. Okay. Now, the third scenario of how radiation can affect the cell is that the cell is damaged, but it's not able to repair itself. Okay? If it can't repair itself, there's a chance that it can live and reproduce. Okay? So in that scenario, we get something called the stochastic effects. Okay? So what that means is the higher the radiation dose, the higher the probability of the occurrence. So in contrast to the deterministic effects, the severity of the adverse health effect is not proportional to the radiation dose. So in this case, we usually talk about like low-level exposures of ionizing radiation over a longer period of time. So that usually infers to things like cancers and malignant tumors and things like that. Okay. So what about the adverse health effects for non-ionizing radiation? Usually, the simple 3 words: deep tissue heating. Okay. Lasers are also considered to be non-ionizing radiation, and because you're able to focus lasers on a very, very small area, it can also do a lot of damage to the skin and eyes. So then how do you protect yourself? Well, that's why we have regulations here at WorkSafeBC, and it's listed in the Occupational Health and Safety Regulation, Part 7. And just to give you some context, and something I didn't know until quite recently, WorkSafeBC actually didn't have regulations on radiation until 1998. So it's kind of surprising, considering that there are a lot of workplace processes that involve the use of radiation. Okay, and just to give you some context, a lot of these regulations are science-based international consensus sort of regulations, because we do make reference to national and international standards. And as well, when it was developed in 1998, we did consult with the Radiation Protection Services, which is now part of the BCCEC, and they also got stakeholder inputs from employers, workers, and other subject matter experts. So regulations includes things like exposure limits, exposure control plan, monitoring, references to national and international standards, and requirements for radiation surveys and specific types of documentation. Okay. So before I actually get into the topic of exposure limits, I have to introduce to you the concept of the different types of ionizing radiation dose quantities. So the first dose quantity I want to introduce to you is something called the absorbed dose. Okay. So what that is the amount of energy that you deposit in a certain amount of matter or a certain amount of material. Now, the unit that we use to measure absorbed dose is called the gray. So 1 gray equals to 100 rads, and rads is usually one of those units the other places in the world like to use, like such as the United States. Okay. Now, 1 gray actually is actually a very, very big unit. So usually you will see units such as milligrays or micrograys. Now, as you may know, that absorbed dose only takes into account the physical consequences of depositing energy into a material. Okay, so it doesn't really explain the health effects or the biological consequences of depositing energy to like a tissue or an organ in the body. So I'm going to introduce you to the second radiation dose quantity, and that's called the equivalent dose. Okay, so the units for equivalent dose is called the sievert, or SV for short. And what it takes into account is something called a radiation weighting factor. Okay, so again, the observed dose is weighted for the degree of the effect of different types of radiation. So as you can see here, alpha radiation and neutron radiation, much higher radiation weighting factors compared to, say, gamma and beta and X-ray photons. Okay. Again, a sievert is actually quite a large unit, so a lot of times you'll see units in terms of millisieverts here. Okay, and sometimes in the United States, you still use a unit called the rem. So here's the conversion factor: 1,000 millisievert equals to 100 rems. Okay, the third and last dose I'd like to introduce to you is the effective dose. Okay, so it doesn't like the equivalent dose that which you saw in the previous slide. It doesn't take into account the differing susceptibilities of the tissues and organs that could be irradiated with ionizing radiation. So again, this is from international guidelines and international consensus standards. The International Commission of Radiological Protection, or ICRP for short, has determined the tissue weighting factors for various organs. Okay, so how do you calculate the effective dose? So you get the absorbed dose, multiply that from the radiation weighting factor, multiply that by the tissue weighting factor, which you see down here, around here. Okay, so you might notice that things like the gonads and the red bone marrow and some parts of the digestive tract, they have a higher tissue weighting factors compared to other parts of the body. That's partly because cells in those areas can reproduce at a much faster rate compared to the other parts of the body. Okay, so since I introduced you to the different radiation dose quantities, I'm going to get into the different exposure limits that different regulatory agencies have. So one regulatory agency that looks after ionizing radiation is the Canadian Nuclear Safety Commission, okay, based in Ottawa. So interesting enough, their exposure limit is up to 50 millisieverts per year, and you're allowed to average it over 5 years, but to a maximum of 100 millisieverts. So that's actually very different from WorkSafeBC's exposure limits, whereby our annual effective dose is only 20 millisieverts. And we do not, unlike the CNSC, we do not permit averaging over a 5-year period. We also have something called an actual level. So that's the level where additional regulatory requirements apply, such as additional workplace monitoring, exposure control plans, and things like that. So our action level is the effective dose of 1 millisieverts per year. Another thing of note is that we actually have dose limits for pregnant workers, and that's 4 millisieverts from the time pregnancy is declared to the end of term. So why do we have that? Again, ionizing radiation, there's no known threshold minimum dose. And then another effect that ionizing radiation could have is something called hereditary effects. So any damage to the chromosomes can cause mutation in the cells. So especially in germ cells where cells can, or cells in the fetus where the cells can divide very rapidly, germ cells can cause a mutation to appear in the baby. Okay. So in the few slides ago, we talked about the somatic effects, especially the deterministic and stochastic effects. But I'm gonna, since I already introduced you the concept of radiation dose quantities, I'm gonna throw you some numbers at you. So this is an interesting statistic. The risk of developing a fatal cancer from a workplace exposure to radiation is 4% per 1,000 millisieverts. So what does that mean? It means that if a worker works for, say, 50 years and is always exposed each year to 20 millisieverts, then they will receive a cumulative exposure to 1,000 millisieverts. So they have a 4% chance of developing a fatal cancer. Now, getting back to inspectional work, when we talk about radioactive materials, all radioactive materials have to be licensed by the Canadian Nuclear Safety Commission. So every time anyone does an inspection on site, they have to have the licensing documents available on site for like officers like myself or other regulatory agencies to see. It lists out the criteria that and how they can operate and the parameters of what they can use in regards to the radioactive materials they're using. Okay. Now, WorkSafeBC, we do have jurisdiction over radioactive materials. So some of the things I've inspected in my past is like nuclear medicine labs, and as well as like non-destructive testing operations that uses something called a gamma camera, which I get into in the next couple of slides. And sometimes we would also do like investigations in regards to reports of overexposures to workers. And then if that's the case, we'll look into things like worker safe work procedures, training and education, and other and their control strategies on how they control exposures. So on the note of non-destructive testing, this is what the exposure device would typically look like. So usually when we talk about gamma cameras, we talk about iridium sources, like radioactive sources such as iridium-192 or cobalt-60. Again, they emit gamma radiation. So usually the radioactive source is stored inside this device, and this is like a cross-section of what it might look like. So the radioactive component is actually this little piece of cylinder or rod over here, and it's actually attached to a flexible rod, and then this can, oh, the mouse is not working. Here it is. So this rod can be extended remotely using safe work procedures through a portal such as this, and then it allows the contractor or the employer or the worker to take non-destructive testing images. So say, for example, you want to see what's behind the wall or what's above the ceiling or what's below the floor without like damaging this. You would use a technique like this, this non-destructive testing equipment. Up north and around the Fort St. John or oil and gas industry, you'll see people using non-destructive testing equipment to inspect the integrity of oil pipelines. For engineering firms, sometimes they like to use this sort of technique of non-destructive testing to check the integrity of, say, a bridge or some big structure like that. So this sort of non-destructive testing application is quite widespread throughout BC. Now we're going to get into X-rays, and this is for all employers under provincial jurisdiction. That's exclusively under the purview of WorkSafeBC, and we make a lot of regulatory references to the Health Canada safety codes. Okay, so X-rays are found in a wide variety of facilities, so medical, dental, veterinary facilities. Again, it's interesting. More and more non-destructive testing devices are using X-rays rather than radioactive materials, probably because a lot of companies do rather not deal with the CNSC. So that's an interesting trend. Something I have to deal with. Other places, food packaging places, laboratories, analytical procedures, X-ray fluorescence equipment, things like that. One interesting thing that's not always under WorkSafeBC jurisdiction is employers under federal jurisdiction. So things like airports, security checkpoints. Every time you go to an airport, you scan your baggage. That uses X-rays. Sometimes that might be considered under federal jurisdiction. So the federal agency in charge of that is called the ESDC. So that's the Employment Services or Social Development Canada. So they do have officers like myself, except they only handle inspections or investigations of employers under federal jurisdiction. Okay. Another thing you should probably know is that if you go on to work in the healthcare industry, you should know two types of diagnostic X-ray imaging equipments. The first type over here is called the radiographic unit. So it's kind of like you go to a dental office, you get one of those one-shot X-rays, bite wing X-rays, or you go to the hospital, you take a chest X-ray, you take a snapshot just to get one image. Okay. The other category of the diagnostic X-ray imaging unit is called fluoroscopy units. So what it does, it continuously emits radiation or X-ray radiation in order to produce a video. So it is quite common in like medical techniques, such as in cardiology or angiography, or sometimes you put a probe down through the digestive tract to see if there's a tumor or not. So that's another major type of X-ray imaging unit commonly found in healthcare. So moving on to non-ionizing radiation. Again, WorkSafeBC, we have regulations in reference to consensus standards. So these consensus standards include the Health Canada Safety Codes, which is updated from time to time, the Canadian Standards Association, or CSA, and as well as the American National Standard Institute, or ANSI standards. Okay. So our regulations also make reference to a phrase called as amended from time to time. So what that means is the latest version of the Health Canada Safety Code, the CSE standard or the ANSI standard would apply, because they do change sometimes every 3 to 5 years, or sometimes it's as long as 10 years before it gets updated. A lot of times the exposure limits and the recommendations or mandatory requirements, they do change over time. So you may notice that here, our exposure limits are usually set in the standards, not in the regulation itself, in regards to non-ionizing radiation. So where do we find non-ionizing radiation? Well, you can practically find it in so many places. So in addition to, say, radar facilities or manufacturing facilities that have radio frequency sealers, with the proliferation of wireless technologies, this Wi-Fi, cell towers, things like that, and a big issue in non-ionizing radiation and occupational health and safety is lasers, because lasers are becoming more and more common in different types of workplaces. Okay. One quick example I'll give to you on the complexities of jurisdiction is cell phone towers. Now, a lot of the telecommunication companies, they're under federal jurisdiction. So again, it's kind of interesting because they still use Health Canada Safety Code 6, which we do cite in our regulation. Yeah? And to even put up a cell phone tower, it has to be approved by Industry Canada, which also follows Safety Code 6, and you also have to follow the municipal bylaws. Okay? Where WorkSafeBC might get involved is, say, sometimes we got a claims investigation, some worker was claiming that they've been overexposed to working in a cell phone tower. We may have to go out there to do some measurements if we're not able to find any radiation surveys or any results from the reported incident. Okay. So I'm gonna have a couple slides on lasers. So what's a laser? So laser is actually an acronym for light amplification by stimulated emission of radiation. Again, I'm not gonna get into too much detail about it, but it's pretty much regulated by a set of standards In general, the parent standard is the ANSI Z136.1 standard, which covers all types of lasers. And then we have two specific standards for healthcare facilities, namely ANSI standard Z136.3 and CSA standard Z386. Now, there are many different classes of lasers. I'm not going to go through every single one of them. The most important thing you probably should know is class 4 is considered the most dangerous type of lasers. Okay, because these lasers are powerful enough to cut sheet metal and cut through different types of materials. Okay, so this is an example of what a class 4 laser system looks like. This is from a laser engraving system, a laser engraving company which engraves like things like trophies and other signs. They use a class 4 carbon dioxide laser. As you can see, they have an inclusion of all these safety and warning signs as mandated by the ANSI safety standards. Again, many different applications in industry and healthcare. So I'm going to briefly go over the different properties of lasers. So when you compare it to ordinary light, lasers are considered to be monochromatic. So they essentially emit one specific wavelength of laser. Now, this is misconception that you can always see a laser, but in reality, a laser such as a carbon dioxide laser with carbon dioxide laser with a wavelength of 10.6 micrometers, it's going to be invisible. So when I do inspections, I have to be careful that if a worker or employer says that you can't see a laser thinking it's safe, that's absolutely not true. Okay, so that's why when I do inspection, I need to know the wavelength of the laser. If it doesn't fall within the visible range, that's something to be aware about. Another unique property of a laser is that it's collimated. So when you shoot a laser, like what you see in Star Wars, it only shoots in one direction, right? So unlike a light bulb, which some of it's on up in this room, it goes in many different directions. Okay, and the other important property of lasers is that it's coherent, it's in phase. Okay, it's not like ordinary light, and where all the electromagnetic waves are not in sync with each other. Okay, so with all these properties in mind, the major health and safety issue is that the lasers can be focused into such small spots on a specific material with very high energies, it can literally damage your eyes and skin. So how do you detect radiation? For the most part, you can't really see it or feel it. So a lot of times you need specialized equipment to measure radiation. So there are many different types of survey instruments like the Geiger-Müller counter or ionization chamber, things like that. And the units that are used to measure radiation is usually in counts per minute or dose rate, which is like microsieverts or millisieverts per hour. And usually the dose rate is what we're most interested in because we're going to be health and safety professionals, right? So different types of instruments and different types of radiation, you need different types of radiation survey equipment. So if any of you are interested after this session, I have one example of what a simple radiation survey equipment looks like. So if you're interested, you just stay in class and I can show you guys. Okay. Then these are some different examples of the radiation detection equipment that are out there in the market. Okay. So then how do you assess exposures to workers? Well, you have to use something called a dosimeter. So dosimeters use cumulative dose, and there are actually two types of dosimeters that are certified by the Canadian Nuclear Safety Commission for external dosimetry. First one is called the thermoluminescent dosimeter, so TLDs for short. It's usually a dosimeter that's quite small, about 5 centimeters by 5 centimeters long. So what it has is a lithium fluoride crystal inside. So when it's exposed to radiation, the crystal actually absorbs that radiation. And when you take it back to the dosimetry service provider, they can determine your radiation dose based on the amount of light emitted from the crystal after they use a specialized heating process. So the TLDs have been used for a very, very long time. They're very, very robust and quite cost effective. One of the newer dosimeters that is recently certified for, I think, about 5, 6, or 7, 8 years now is called the optically stimulated luminescent dosimeters. It works in a similar fashion to TLDs, except that they use something like aluminum oxide sort of material to absorb radiation. And instead of using heat to determine the amount of radiation being absorbed by the dosimeter, they use like a specific type of a light, such as a light emitting diode. So for Canadian workers, there are 3 approved dosimetry service provider. The first one is the only Canadian one, is the National Dosimetry Service, or NDS, Health Canada, based in Ottawa. The 2 other dosimetry service providers are based in the US, is Landauer and Global Dosimetry Solutions, based in California. Now, every time you submit your dosimeters, you have to not only submit it back to the dosimetry service providers, but they also have to submit the numbers back to something called the National Dose Registry back in Ottawa. And these are legal results, and it sticks with the workers for their entire lives. Okay? So a lot of times when we do radiation inspections, sometimes we assess the effectiveness of how good the dosimetry management program is. So some of the things we kind of see is sometimes they might not wear the dosimeters properly, or sometimes they may not wear it when they're supposed to wear it. Other times, workers might share the dosimeters when you're not supposed to. So these are some of the things that we like to look for when we do inspections. So what does the National Dose Registry do with all these numbers? Well, they like to use it and compile databases. So just to give you some examples from the most recently publicly available report from the National Dose Registry. As you can see here, occupations such as dentistry or physicians, they usually have pretty low occupational ratings in terms of ionizing radiation. Jobs such as the nuclear medicine technologist or industrial or radiographer, or if you're working in the uranium mine, a bit higher. But then when you compare it to, say, some of the doses you might encounter every day, it's actually still pretty low. So if you get a dental x-ray, that's 0.005 millisieverts. In comparison, the annual background radiation we all receive in Canada on average is 1.8 millisieverts. Some places in Canada is a bit higher. Vancouver is slightly lower. If you want to get your head checked with your CT scan, 2.0 millisieverts. Now, what you see down here is like very, very acute exposures within 24 hours. So if you have, say, for whatever reason, 100 millisieverts of exposures within 24 hours, you can get damage to different parts of the organs. 1,000 millisieverts, we're getting into radiation sickness, and then 5,000 millisieverts, potentially a fatality. So how do you control exposures? The key principle is ALARA. So ALARA, I think a lot of you probably already know, as low as reasonably achievable, and that's right in our regulations here. So the 3 basic concepts of radiation protection is time, distance, and shielding. Okay? So you try to minimize time, working with the radiation source, trying to maximize the distance, like be as far away as possible, and you try to incorporate shielding wherever possible. A couple other key concepts you should probably know. When we talk about point sources and distance, you'll hear something called the inverse square law. So what that really means is if you double the distance that you're working from the radiation source, you're essentially reducing you reduce the dose or exposure by a factor of 4. So if you triple the distance away from the radiation source, you reduce the dose or exposure by a factor of 9. Okay? And then when you're dealing with radioisotopes, you have to also consider the radioactive decay and its associated half-life. Now I'm going to talk a bit about shielding because there's a lot of misconceptions about shielding and radiation. So there's no one-size-fits-all sort of solution when it deals with shielding and radiation. Different types of radiation, different types of ionizing radiation interact in different ways with shielding materials. Here's a quick diagram to help summarize everything. So alpha particles can essentially be stopped with a sheet of paper because it has mass. Beta particles, which are essentially electrons, you need a certain thickness of wood or a certain thickness of plastic. They advise not to use heavy materials such as lead, otherwise you're going to get a lot of residue X-rays from all the interactions between the beta particles and the lead material. When it comes to gamma rays or X-rays, it's usually things like lead or concrete. So another specific thing you should know about shielding is something called a half-value layer. So that's it's like when you have an absorber that's a certain thickness that's required to reduce X-ray photons or gamma ray photons to 50% of its initial intensity. Again, there's a misconception that shielding can stop gamma rays and X-rays, but in reality, it can only be attenuated. You can only reduce the intensity. Okay, to keep things in perspective, 7 half value layers can reduce the initial intensity of X-rays to 1%. And likewise, when you have 10 half value layers, reducing the intensity to 0.1% of its initial intensity. So, and what's a half value layer? Usually in lead, you're talking about millimeters. When we talk about concrete, we're usually talking about centimeters. So the specific numbers is usually found in the appendix of the different Health Canada safety codes. So controlling exposures, what do you expect to see? What do I expect to see in radiation safety programs? Well, just follow the regulations, and this is where where we reference standards. So when I do an inspection, I want to look at the radiation safety program. I'm going to ask you, who's your radiation safety officer? Who's coordinating everything? Okay, because someone has to be in charge of the radiation safety program at your workplace, right? And then I don't expect people to memorize the like a 100-page standard or the 100-page safety code. The important thing is you need to have a current copy of the standard safety code on site, and you need to be able to know where to find the information. Okay. The other things I like to look at is radiation surveys, inspections, investigations, what kind of personal protective equipment you have, safe work procedures, monitoring equipment, your dosimetry management program, things like that. I'm going to talk a bit more about radiation surveys because it's one of the things I like to look at. So what a radiation survey is, it's an evaluation of the safety systems in place at your work site, and it has to be conducted by a qualified person. Okay. So some of the information a radiation survey would typically include is a description of the type of X-ray equipment that you have at the workplace. Have you done leak testing? Is there any issues with it? Any problems with it? Can you estimate the occupational dose of the worker? How's the personal protective equipment? Is there any damage to the personal protective equipment? An assessment of the education training of workers, things like that. Okay, so how often is a radiation survey needs to be done? Well, it depends on the safety code. Usually it could be every 3 to 5 years. The exception to that is in our regulations, if the equipment has been damaged or modified in any certain way, you really need to get it done as soon as possible. Because if there's damage, it's that risk of radiation leaking right into the workplace, affecting workers. And then occasionally we'll get a notification of unusually high exposure to a worker at the workplace. So if that's the case, we need assurances that the radiation safety program that you have, it's intact. So one of the things I like to look at is the radiation survey. Is there any problem with the equipment, any leakage of X-rays, things like that? So it looks like I have time to do a case study. Oh, really? Oh, I went faster than I thought. Okay. Okay, so one of the emerging issues is how it's happening in dentistry, but this is going to filter out into the healthcare, into a lot of different medical facilities. It's a new X-ray imaging technology called the cone beam computed tomography, or CPCT units for short. So I'm going to compare this to the conventional so-called two-dimensional bite wing X-ray imaging. So when we do like a risk assessment, think about how these pieces of X-ray units work. Okay, so I'm sure all of you have been to a dentist recently or had an X-ray done. So usually when they do a 2D image, it's like a one shot, one image sort of thing. So that's called a bite wing X-ray unit. Okay, so again, one snapshot for each patient's teeth for each X-ray image. Very, very short duration, one direction. Okay. So when we talk about the cone beam CT X-ray units, we're talking about 3D imaging. So these units is where the X-ray unit actually rotates around a patient's head. Okay, so it's unlike the bite wing, it's not one direction. Potentially, you're like emitting X-rays in a 360-degree orientation. In addition, you're also emitting the X-ray unit is actually on for a much longer period of time. So again, a higher potential for X-ray emissions and higher potential for X-ray scattering. Okay, so what kind of dosimetry data that we have and for these two X-ray units? Well, one thing we like to do is compare, check out the historical dosimetry data through the National Dosimetry Registry, National Dose Registry back in Ottawa. Okay, so the bite wing X-ray unit has been used in a lot of dental clinics in Canada for many, many decades. So a lot of times the reported occupational exposures is usually not detectable or if they do detect something, it's usually well under 1 millisievert. So unlike the cone beam imaging technology has actually only been around for, I guess, maybe 5 or 10 years. And then currently there's only, out of the 2,300 dental practices in BC, only 200 dental practices actually have this cone beam unit. And that means less than 10% of all dental clinics actually have this new imaging technology. So if we look at the historical dosimetry data, you can argue that the historical dosimetry data is not reliably predictive of what you would expect workers to be exposed to from X-rays being emitted from the cone beam CT units. So how do you control exposures? Well, with respect to the bite wing, to the X-ray imaging, we have the health and safety regulations along with the Health Canada Safety Code 30, which applies to dentistry or dental facilities. Okay, so a lot of the standard practices and safer practices apply. So you may notice when they take an X-ray of you, they might stand behind a drywall or stand far away and use a remote or use some sort of remote control on the wall to ensure that they won't be overexposed to radiation. So that's kind of like standard practice for a 2D bite wing X-ray imaging work process. In contrast, the cone beam CT scan. Yeah, I mean, you can stand far away from the X-ray, but I mean, if you don't have proper shielding, then there's a pretty good chance you may be exposed, right? Because there's a chance that the cone beam CT unit, when it rotates around the patient's head, it can expose the worker, right? So a lot of so what we like to see is like what kind of engineering controls you have. Is it enclosed in a shielded room? Okay, and for the most part, we've been finding that a lot of dental clinics they have a dedicated shielded room just for like a cone beam unit. However, there's a few dental clinics where they don't have proper shielding and they rely more on distance, so that's something that we have to deal with. Okay, another thing to take into account is, do you really have to use the cone beam CT scan? Can you use existing like two-dimensional technologies such as the bite wing to get what you need? Another thing is like, can you reduce the amount of radiation being used? Like, do you have to really do a 360-degree scan of a patient, or can you just get away with doing a 180-degree scan, which in some cases it is possible. And with the newer cone beam CT units, their sensors and detectors are much more sensitive, so that also enables to use a lower powered X-ray unit. So we can talk more about it in the question and answer period if you want. Okay, so here's some selected occupational health and safety resources on radiation. So in addition to our regulations and guidelines, I provided you guys a link for the BC Centers for Disease Control and the radiation portal, as well as the Canadian Nuclear Safety Commission. They have a lot of great resources on occupational health and safety and radiation. Okay. So hope you learned a thing or two from my presentation. So I'd like to thank a lot of people who made this presentation possible. And any questions?
Great, thank you, Mark. That was a really informative presentation. And does anyone have any questions?
Hello. Thank you for the talk. I just had a quick question for you. Are airline workers, like flight crews and stuff like that, are they classified as radiation workers?
That's a good question. First of all, airline workers, they're under federal jurisdiction. Second of all, I know that certain airlines, they actually started an extended dosimetry program. So the results so far indicate they're not considered to be nuclear energy workers. The criteria for nuclear energy workers is the worker has to be exposed to 5 millisieverts or more. So far, the results that I've seen show that they're well below that limit. Yeah.
Thank you.
I am curious as to whether WorkSafe tracks the use of lasers in non-medical settings, like beauty places and spas where we see them being used much more over the past years.
Yeah, that's a good question. We've been getting a lot of calls from like the public health regulatory agencies regarding lasers, and yeah, like if you to answer your question, like do we specifically track every single laser system in the workplace? No, we don't. A lot of times we rely on other regulatory agencies or other associations or colleges to do that. A lot of times these issues come to attention to say a phone call or some interactions with other agencies. So.
Hi, Mark. My dentist uses the cone beam technology,
Yeah.
and from what I remember, it's kind of it's only in a semi-enclosed area, sort of like a little enclave. So it seems like it's not in a completely isolated enclosed room.
Yeah,
So
we,
what
we,
would you
we
say
yeah,
to that?
that's a very good point. We do notice that even though a lot of the dental facilities have the cone beam in a totally shielded enclosed area, but there are a few dental practices that don't totally enclose the cone beam. So yours might be one of them. Maybe after this presentation, you might talk to me about that. Okay?
I've got two related questions. My first question was you said that there's X-ray use in food packaging.
Yeah.
Can you what's the application there?
Yeah, it's more to sometimes in some food facilities they like to irradiate meat to destroy the some of the bacteria and all that.
Okay.
Yeah.
It's a sanitization.
Yeah.
Okay.
Yeah.
And then my next question is sort of more general in that you have a lot of different workers exposed to a lot of different types of radiation.
Mm-hmm.
How well informed do you generally find workers, and where are the gaps?
Yeah, usually say in a healthcare facility, we usually find that they have a pretty good health radiation safety program. They're pretty sophisticated. Usually the challenge in many healthcare facilities because sometimes they have a huge number of people and then with so many different works and so many different shifts. I think one of the big challenges for them is managing their dosimeter, the dosimetry management program. In terms of education training in like healthcare facilities, I found that on average is not too bad. Now, when it comes to industry, it's a bit of a like manufacturing is a bit of a different story. Sometimes they may not even know what the requirements are, but you got sophisticated employers that kind of know everything. So it's a broad range of employers that have a broad range of awareness and knowledge on radiation safety. Yeah.
Hi there, really interesting talk. I just had a question because when we go to the dentist, we get the lead aprons or things
Right.
to protect us. And I know that the hygienists and the dentists don't necessarily spend a lot of time in, as you mentioned, as a control, they stand behind a wall.
Mhm.
I was just wondering though, for those other professions that have higher dosimetry data, what kind of engineering or PPE is usually available to them?
Yeah, it depends on what type of facilities. Like the different Health Canada safety codes, they have different requirements of shielding. Like some facilities they require like a total enclosure or total shielding, but others it's more like a recommendation, not a mandatory requirement. In terms of PPE, it really depends on the work process. Like sometimes workers, like say in a fluoroscopy unit in a healthcare facility, they have to wear not only lead aprons, but they have to wear like lead collars and other like other types of PPEs. And a lot of times they have need to have a check of the PPEs, make sure it's not broken or there's no cracks. So it's a wide range of requirements depending on the application and the workplace.
Okay, I've got a few online questions I'm going to go through here. The first one is, how do the other WorkSafeBC OHS regulations apply in federal jurisdictions, or are they completely exempt from all WorkSafeBC regulations?
Yeah, so I cannot enforce regulations on employers under federal jurisdiction.
Okay, that was simple. Any potential health effects to organs or eyes from using microwaves to heat up foods every day?
No, I wouldn't worry about that. Usually, the why you use a microwave, the amount of energy being emitted, it's so low. It's not really too big of a deal. Yeah.
Okay. And finally, can you comment on radon exposure and what sectors and job positions are prone to such exposures?
Yeah, it's a good question. Radon is one of these emerging issues. Put it this way, there's a huge demand for many different places to remediate radon. So usually the people most at risk is the people who have to do the remediation of radon themselves. So it's one of those things that we're keeping an eye on very, very closely. With respect to exposure limits to radon, we don't really have a direct exposure limit to radon other than our ionizing radiation exposure limit of 20 millisieverts per year.
I have a question. In the workplace, there's a variety of different people working with different characteristics. Are there any subpopulations which might be more at risk to the effects of this radiation in the workplace, or like is everyone sort of in the same boat?
Well, as for risk factors, probably if we're just talking about workers, like do you mean like specific types of like jobs or a specific type of person? Susceptibilities. Well, okay. So like obviously, if a worker is pregnant, it's going to affect the baby, right? So that's one segment of the population. It's probably the best way to answer this question is I use it by analogy. So like when during the Fukushima nuclear incident, one thing that they took into account is a person's age. Like who's going to clean up the radioactive waste or the radioactive mess in the Fukushima nuclear power plant. What they end up doing is they got the older workers to go in to clean it up because statistically they'll probably die of something else rather than dying from a radiation-related disease. So that kind of implies that they don't want to send in younger workers because if they're exposed to such elevated levels of radiation, that kind of gives them an elevated risk to have adverse health effects due to radiation sometime down the road. So yeah, so age is another factor.
Yeah, wondering about laser surgery. I understand there's a certain amount of lasers used in surgical procedures. Have there been reports of injuries to operating room personnel from those surgical lasers?
Yeah, it's kind of interesting you mentioned that because there's some peer-reviewed articles that mention like surgeons themselves, sometimes they've been infected not directly from the lasers themselves, but things like from laser-generated airborne contaminants, like some of the biological or chemical hazardous materials that are emitted. Some jurisdictions I know they have doctors that file claims because they got some sort of disease from laser-generated airborne contaminants. Yeah. But not from the laser energy directly. No. I think another big hazard is fires and explosions. For some, because sometimes you have to use an optical fiber laser, a laser. Say you stick it down a person's digestive tract or something like that. And you have laser source with a potential ignition source, and you have oxygen and a fuel source. There have been some reports, I think it's 1 or 200 incidents, I think in North America, where the patient literally just catches fire. Yeah, it's pretty sick. Yeah.
That's a bigger hazard to the patient than the doctor, though, right?
Exactly, yeah. But then, I mean, the workers, they have to know what to do, right? Because they don't want to catch fire themselves, right?
True.
So that's why in the 2 most recent health and safety standards in lasers, they have specific mandatory requirements on this sort of issue. Yeah.
If I could ask one more. People doing laser hair removal, is any incidence of injury resulting from those lasers?
I'm sure there is, but I haven't heard any specific ones. Yeah.
I believe in the oil and gas industry, they use these radioactive gauges, I guess, to monitor certain processes.
Yeah.
So in that case, like WorkSafe has jurisdiction over oil and gas, but they also have, so does the Canadian Nuclear Safety.
Yeah.
Commission.
So yeah, that's a very good question. In practice, Yeah, we have overlapping jurisdictions. Usually, we let the CNSC do their job first because their requirements for using and handling radioactive materials is much more prescriptive than us, and that's why you'll see if you go on site, the CNSC will issue a license on saying what they can do, what they can't do. Okay, so if the CNSC actually sees a violation in the licensing agreement, then they have the ability to stop everything. And we would also get involved. Sometimes I would coordinate with my counterpart, my CNSC counterparts in the office in Calgary, see if there's any issues that where we can do joint inspections or joint work together. So yeah.
Okay, another online question. Is there any production of radioisotopes in BC?
Well, this Triumph. And then I think actually that's a good question. And another emerging issue you might want to be aware about is historically a lot of the medical isotopes are produced in the Chalk River facility near Ottawa. There's newer emerging technologies using particle accelerators to produce certain types of medical isotopes on site. So you may see all these mini particle accelerators coming online sometime in the future in certain healthcare facilities where they can produce medical isotopes on site. Yeah.
Is there such a thing as a respirator approved for use with radioactive contamination?
Well, not exactly. We do have a CSA standard for respirators itself, and which we do reference in the regulation. The general rule of thumb is that we follow what the CNSC usually does. The CNSC, they actually have specific guidelines on when to use a respirator, especially when handling radioactive materials. So usually I would defer them to the CNSC guidelines. Yeah.
And one final question from online. Will more and more high-rises that use underground materials, sorry, my question disappeared as I was trying to read it. In a city, increase the environmental radiation to the general public?
Can you repeat the question?
So materials that are being brought up from the earth and used to build high-rises, does that create more exposure in the general atmosphere?
Yeah, one thing I didn't go over is something called NORMS, which is an acronym for naturally occurring radioactive materials. So a lot of the naturally occurring radioactive materials comes from underground. So if the person who asked that question is talking about that, then yeah, there's that potential elevated risk for sure. And we quite see that quite often in the oil and gas industry when they try to extract oil and gas from the ground. Yeah.
Okay, we're going to squeeze in one more question quickly.
Is a research from Japan. They say that cell phone Wi-Fi microwave is strong enough to liquidify gel substance that in your body. So I don't know, maybe I can't remember exactly, but I think they were mentioning about lubricant that in joint liquefies and comes out of, I don't know where. Is it possible?
Yeah, I have to know more details about that study. That's the first I've heard of it. Yeah, usually when you want to refer to the potential health effects of different types of radiation, I would usually defer to the different types of national and international consensus standards and guidelines. And to the best of my knowledge, I never heard anything like that from those resources. Yeah.
Okay, well, that ends our seminar today. So thank you, Mark, for taking your time to come speak with